This video is a demonstration of a conical pendulum and an investigation into the physics behind it. Firstly, we need to discuss a simple harmonic pendulum. A mass is attached to a piece of string and moved from equilibrium. When released, the resulting motion of the mass will be simple harmonic motion. The period of this motion, or the length of the string, can be determined from the equation shown here. However, if a tangential force is applied, the mass and string will move in a horizontal circular path, and different equations of motion must be used.
To model the motion of a conical pendulum, there are a few key equations to understand. The first of which is the equation for centripetal force when looking at circular motion. This equation is F equals mv squared over r. As well as this, as shown in the diagram, we can resolve the forces to create another equation for F. From the diagram, you can see that F will be t sine theta, but we don't know what t is, so we'll also need to take the vertical component and equate it with the downwards force acting on the mass to calculate t. From this, we get t is mg over cos theta, and therefore, after combining the equations, we get F equals mg sine theta over cos theta, or mg tan theta. From here, we can equate the original equation with this equation for F to get mg tan theta equals mv squared over r. Clearly, the m values cancel, leaving us with g tan theta equals v squared over r. For our investigation, we're looking to work out r, so we'll need to work out v in terms of r. So, if we take the distance around a circle and divide it by the time period for one complete rotation, we get v equals 2 pi r over t. We can now put this into our equation, remembering to square it, and we get g tan theta equals 4 pi squared r squared over t squared r. Simplifying this to g tan theta equals 4 pi squared r over t squared. If we rearrange for r now, we get r is g tan theta t squared over 4 pi squared.
In our laboratory investigation, a simple setup to demonstrate a conical pendulum was used, as shown here. A circular motor was used to provide a constant speed to the attached mass, allowing it to rotate in a horizontal circular path. A clamp and stand were used to suspend the circular motor above the table. Background boards were used so that the mass would be visible on the tracker software and to remove any background interference that would interfere with the detection of the ball on said program. This is useful if more data was needed to be gained from the videos. After videos on this setup were recorded, the same setup was used, however a light was placed behind the path of the ball. This is to simulate how planets are detected via the transit method, where light from stars is blocked by a planet transiting in front of them. And from the data of how large the dip in the intensity of light from the object is, important data about the planet can be determined. However, in our simple setup, only the time period of the transit can be determined directly from our videos. The main limitation in our setup was that the motor used in this experiment had a diameter, meaning that the length of string which we measured is not the length of the theoretical pendulum. However, to simplify the calculations, the full length was not determined and this was disregarded. Would you set up the experiment in a similar way? What changes would you make?
To obtain the data from this setup, the motion of the pendulum was filmed for 10 full rotations 5 times. From these videos, the time for these 10 rotations was recorded. This was done 3 times per video, so that an average could be calculated, and then the average for the 5 videos was then worked out. From this, the time was divided by 10 to get a time for one complete rotation. Then the videos were looked through frame by frame, and the best frame to record the angle was chosen. Each of the videos had an angle recorded, and the average angle was then taken. This came to 51 degrees. From this, the radius could then be calculated, although there is no easy way to tell if this value is what we would expect. However, if we use some trigonometry, we find that the length of the string is r over sine theta, so we can measure the length and see if this is close to the calculated value from our equations. We measured the length of the string to be 15.6 centimeters and calculated it to be 16.02 centimeters. So from this we can see that the model is fairly accurate.
The conical pendulum rotates the mass in a horizontal circle, not unlike the motion of objects around a gravitational source. In fact, these equations for the time period of a pendulum and the time period of an orbiting body are quite similar. However, different data is used to determine and solve these equations. With advancement of telescope technology, scientists are able to view the transit of a planet across the star and determine variables such as its time period of orbit and relative size just by looking at how the light intensity from the star decreases when the planet is transiting. In our simple lab experiment, we have used the same setup as stated before, but we attached a light source to the backing boards, which was behind the path of the rotating ball. We show from the video files generated that the time period of the orbit can be deduced from these videos without the use of complex mathematics.
The maths behind the circular motion of a planet around a star is very similar to that of the conical pendulum. Some equations are in fact the exact same. For example, F equals mv squared over r and v equals 2 pi r over t. However, we can now have a new equation, F equals g big M small m over r squared, where big M is the mass of the star and small m is the mass of the planet. If we equate these two equations for F, we can work out that v squared is mg over r. Using the equation for v, we get 4 pi squared r squared over t squared equals mg over r. If we arrange this for r, we get r cubed is mg t squared over 4 pi squared. However, we still have the mass for the star in this equation, so do you think there's any way we can work out this mass from the observations taken? There actually is. There's a relationship between the mass of a star and the luminosity of this star. So using the time period as well as the luminosity of the star, we can now calculate the distance the planet is away from the star. If we could observe the Sun from a far off point and measure the time period for the Earth to orbit, we could then calculate the distance the Earth is away from the Sun. This is also known as 1 astronomical unit, and if we substitute the values for the mass of the Sun and the time for 1 year in seconds into the equation, we get r is 1.495 times 10 to the 11 meters, which is pretty much exactly 1 astronomical unit. Overall, you should be able to see that the conical pendulum is quite a simple system to mathematically describe, and its motion is quite simple. It's also a very fundamental system to understand, as it has lots of very important applications such as orbiting bodies as explored in this demonstration. Can you think of any other places where this kind of motion appears?